Hello and welcome back to Calculus, the series where we explore differential equations. In today's part 32, we'll take a look at homogeneous differential equations and how to tackle them. However, before we do that, first, as you already know, I'd like to thank all the nice people that support this channel by liking and subscribing. To begin today's video, I would like you to consider a differential equation in the form of x times dy over dx is equal to x plus y. I want you to ask yourself, is this solvable using separation of variables like we did in part 30? You could try to move things around, however, because of this plus sign, we're unable to put all of the x's on one side and all of the y's on the other, ensuring that both dy dx are on different sides of the equation and also in the numerator. In the definition of part 30, we discussed that a differential equation begins with dy dx equals to. However, in our case, we have an x multiplied in front. So I think we can agree first, I can divide all of the terms here by x. This should then yield the result of dy dx is equal to 1 plus y over x. Now, since everyone hates dealing with fractions, we can introduce a new variable, let's call it v, and we set it as y equal to x, basically a substitution. So with this substitution, our differential equation now has become dy dx equals to 1 plus v. However, it may seem like we made things worse, because instead of having two variables, y and x in the beginning, we now have three variables, y, x, and v. So that means we need to solve this problem. I need to somehow find another way to rewrite dy dx in terms of this new variable v which we introduced. So now I will reuse our substitution. I think we can agree that we can multiply both sides by x in order to get rid of the fraction. So now we have y is equal to v multiplied with x. And then I can differentiate this implicitly from both sides. So on the left-hand side, all I have is dy over dx. And on the right-hand side, since I have multiplication of v and x, I can simply use the product rule for differentiation. This will give me v plus v prime of x. Now I will rewrite v prime as dv over dx, a more mathematical and calculus way. So now I want you to notice one thing. We have two different expressions for dy dx. One right here, 1 plus v, and another one down here that we just got using the substitution. So if both of these expressions are equal to dy dx, that means I can technically just equate them to each other. So now we have v plus dv dx times x is equal to 1 plus v. And I think we can all agree the v's can simply be cancelled out. So what we have left is dv over dx times x equals to 1. And now we can solve this using separation of variables. What I get is dv equals to 1 over x dx. And finally now I can integrate both sides. On the left-hand side, we're basically integrating a 1, so what you get is just a v. On the left-hand side, we have a v. On the right-hand side, we will get ln of x and of course a plus c. And now finally, I can replug the substitution we used, since v is just equal to y over x. And please remember, our end goal is to have y equals to and everything else on the other side. So that means I can multiply this equation here by x, and all I have left is x times ln of x plus c. And here we have managed to solve this differential equation, which originally was inseparable, and then we used a substitution. Whenever we use a substitution like this, v equals to y over x, the differential equation is going to be called a homogeneous differential equation. So now that we know how it works, let's quickly write down the definition. The definition states that a differential equation in the form of dy over dx equals to f of y over x is called homogeneous. And we solve it using a substitution v equals to y over x. Alright, so now that we have got the definition down and a little example, let's take a look at a more complex example which has an initial condition so that we can find that c in the end. Here we have our differential equation and the initial condition given to us, which states if we plug in x into the y function, we'll get a 4. This will help us find that plus c in the end. Now, firstly, before we divide everything by x, inside of the parentheses, this can be simplified to ln of x divided by y, the rules of logarithms. And then I can divide everything by x. Now we can set our substitution v is equal to y over x. Please note that inside of the logarithm, it is flipped. We have x over y. However, that is not a big deal because technically 1 over v is going to be x over y. So that means this differential equation can be rewritten as v times the natural log of 1 over v. And then for the mini steps here, ln of 1 over v is simply ln of v to the power of negative 1. And again, using the rules of logarithms, we know that this negative sign can go in front. So technically, this whole expression here can be rewritten in a more simple way, specifically negative v ln of v. Now we head back to our substitution and we multiply both sides by x. And what we get is y equals to v of x. And then we implicitly differentiate this equation, which gives us v plus dv over dx times x. Once again, we have two expressions for dy dx, which means I can equate them. This is a differential equation we have now. However, that still doesn't look very separable. So I can divide everything by v. Now I can move this one to the other side. And now this differential equation here is going to be separable. Please excuse my clumsy mistake. Everything here should be dv and dv. And now I have moved everything in terms of v to the left-hand side and everything in terms of x, the right-hand side. So that means I can integrate both sides. I won't go into the specifics of the integrals, however, on the left-hand side, I can tell you that you can use a substitution u equals to ln of v plus 1 to solve this integral. And you should get ln of ln v plus 1 equals to negative ln of x plus c. Now at this point, we can use the initial condition that was given to us in order to find the value of c. However, before we do that, I do have to replug v back. The initial condition now can be employed. Everywhere where we have an x, we place a 1, and everywhere where there's a y, we put in a 4. Please note one thing, when you plug in 1 into the natural log, all you get is going to be 0. So on the right-hand side, only c remains. And this is going to be the value of our c. Rewriting the entire expression, we get double natural log of y over x plus 1 is equal to ln of ln 4 plus 1 minus ln of x. However, the right-hand side can be simplified using the properties of logs and rewritten as ln of ln 4 plus 1 divided by x. This will make our lives a bit easier since we have the natural log on both sides. We can simply cancel at least one of them out. All that's remaining was what was in the parentheses. Next, I move the plus 1 as negative 1 to the other side, and of course integrate it into one fraction. And now finally, I can get rid of this natural log on the left-hand side. What I get is e raised to the power of this entire blue function is equal to y over x. And finally, y is simply going to be equal to x times this entire expression. And there you have it, we have solved this differential equation without a plus c in the end because we were given an initial condition. Solving differential equations like these definitely does require some practice, and I'd like to leave you two practice problems to solve on your own. One of them without an initial condition and the other with an initial condition. If you want to check whether you solved them correctly, go to the link below, which allows you to access the PDF version of this lesson. The other link below is for the folder of PDFs with all 32 parts of calculus that we have done so far. So this is it for now, and next time I will introduce another form of ordinary differential equation, which is handy to learn how to handle. So I hope to see you there and have a nice day. Bye!